Application to symmetrical curves, circles, and ellipses. Welcome, everyone. To begin today's lesson, let's take a moment to reflect on what we have already covered. In our previous sections, we explored the fundamental technique of using definite integrals to calculate the area trapped under a curve. Now, as we move into more complex shapes, you'll notice that calculating the area for closed geometric figures, such as circles and ellipses, can become mathematically tedious and quite cumbersome if we try to integrate the entire shape all at once. However, there is a much more elegant way to approach this. In this lesson, we are going to utilize the property of symmetry. By identifying how these shapes are balanced across the axes, we can simplify our integration process significantly, making much more complex problems much easier to solve. Understanding the concept of symmetry. Think of symmetry as a mathematical shortcut. Instead of tackling the entire complex figure at once, symmetry allows us to focus our calculations on just a smaller, much simpler portion of the shape. Once we have found the area of this small piece, we simply multiply that resulting area by a specific constant to recover the total area of the entire figure. This is particularly useful for shapes that are symmetric about both the x-axis and the y-axis. In such cases, the entire figure is divided into 4 identical, equal quadrants. So, instead of the heavy lifting required to integrate from the leftmost point of the shape all the way to the rightmost point, we can follow a much smarter two-step process. First, we calculate the area of just the region located in the first quadrant. That is, the area where x is greater than or equal to 0 and y is greater than or equal to 0. Second, we take that area and multiply it by 4. The real beauty of this approach is how much it simplifies our integration limits. Rather than dealing with complex boundaries, we can usually change our limits of integration to start at 0 and end at the radius or the semi-axis. This sets us up perfectly for the next few slides, where we will apply this exact logic to derive the area formulas for circles and ellipses. Now that we've established that calculating the area of closed shapes like circles can be quite a tedious task using standard integration, let's look at a much more efficient strategy: understanding the concept of symmetry. Area of a circle. First, let's recall the definition. A circle is simply the set of all points that stay at a constant distance, which we call A, representing the radius from a fixed center point. If we place this center at the origin of our coordinate plane, we can represent the circle using the standard equation: x squared plus y squared equals a squared. To find the area using integration, we need to follow a step-by-step derivation. In step 1, we need to express y as a function of x. Since we are using vertical strips to find the area under a curve, we need to solve our equation for y. If we subtract x squared from both sides, we get y squared equals a squared minus x squared. Taking the square root of both sides, we get y equals the square root of a squared minus x squared. Now, for the purpose of our calculation, we will focus on the upper semicircle, where y is positive. Next, in step 2, we identify the region of symmetry. As we discussed in the previous slide, we don't need to integrate the entire circle at once. Because the circle is symmetric about both the x-axis and the y-axis, we can simply focus on the first quadrant. In this region, our x values vary from 0 to the radius, which is a. Finally, in step 3, we set up the integral for just this one quadrant. We'll call this area a subquadrant. To find it, we integrate our function, y, with respect to x, using the limits from 0 to a. This gives us the integral from 0 to a of the square root of a squared minus x squared, dx. Now that we understand the power of symmetry from our previous slide, let's put it into practice by deriving the area of a circle. In the next slide, we will apply the integration formula to solve this integral and find the total area. Area of a circle, continued. In step 4, we need to apply the integration formula. You'll notice we are dealing with the integral of the square root of a squared minus x squared. With respect to x, the standard formula for this is x over 2 times the square and square root of a squared minus x squared plus a squared over 2 times the inverse sine of x over a. We are going to evaluate this expression using the limits we established earlier, specifically from 0 to a. Moving to step 5, we evaluate these limits. First, let's plug in the upper limit, where x equals a. When we substitute it into the formula, the first term becomes over 2 times the square root of a squared minus a squared, which simplifies to 0. For the second term, we have a squared over 2 multiplied by the inverse sine of 1. Since the inverse sine of 1 is pi over 2, this whole term simplifies to pi a squared over 4. Next, we plug in the lower limit, where x equals 0. Here, the first term becomes 0 because of the x multiplier, and the second term becomes 0 because the inverse sine of 0 is 0. Therefore, the area of just this single quadrant, which we'll call a quad, is exactly pi a squared over 4. Finally, in step 6, we bring back the concept of symmetry that we discussed at the beginning of the lesson. Since we only calculated the area for one quadrant, we must multiply this result by 4 to cover the entire circle. When we multiply 4 by pi a squared over 4, the 4's cancel out perfectly, leaving us with our final, familiar formula for the total area, pi a squared. Now that we have set up our integral for the first quadrant in the previous slide, let's move on to the actual calculation. In the next slide, we will apply this exact same logic to find the area of an ellipse. Area of an ellipse. Now that we have successfully derived the area of a circle, let's move on to a slightly more complex shape, the ellipse. You can think of an ellipse simply as a circle that has been stretched out along one of its axes. The standard equation for an ellipse centered at the origin is x squared over a squared, plus y squared over b squared, equals 1. In this equation, A represents the semi-major axis, and B represents the semi-minor axis. To find its area, we will follow a similar step-by-step derivation as we did with the circle. In step 1, our goal is to express y as a function of x so that we can integrate. We start by isolating the y term. We subtract x squared over a squared from both sides, which gives us y squared over b squared equals 1 minus the fraction x squared over a squared. Next, we multiply both sides by b squared. This gives us y squared equals b squared times the quantity 1 minus the fraction x squared over a squared. If we find a common denominator inside the parentheses, we can rewrite this as y squared equals b squared over a squared, multiplied by the quantity a squared minus x squared. Finally, by taking the square root of both sides, we get y equals the fraction b over a times the square root of a squared minus x squared. In step 2, we need to identify our region of symmetry. Just like the circle we studied in the previous slide, the ellipse is symmetric about both the x-axis and the y-axis. This is great news because it means we don't have to integrate the entire shape at once. Instead, we can focus our calculations on just the first quadrant, where x ranges from 0 to a. Once we find the area of this single quadrant, we will be able to multiply it by 4 to find the total area, as we will see in the next slide. Area of an ellipse continued. Now that we have expressed the function for the upper boundary of the ellipse in the previous slide, let's move on to step 3, where we set up the integral for just one quadrant. To find the area of this single quadrant, we will integrate our function, b over times the square root of a squared minus x squared, with respect to x, using the limits from 0 to a. Moving on to step 4, we can make our lives much easier by factoring out the constants. Since the fraction b over a does not depend on x, we can move it outside of the integral sign. This leaves us with the integral from 0 to a of the square root of a squared minus x squared. With respect to x now, if you recall our derivation for the area of a circle from a few slides ago, you'll see that this specific integral is exactly what we just solved. We already know that the integral of the square root of a squared minus x squared from 0 to a evaluates to pi a squared over 4. This brings us to step 5, where we evaluate the area of the quadrant. We simply multiply our constant, b over a, by the result we just mentioned, which is pi a squared over 4. When you multiply these together, one of the a terms cancels out, leaving us with the simplified expression for the quadrant area, pi a b over 4. Finally, in step 6, we calculate the total area. Remember our core principle of symmetry from the beginning of this lesson. Since the ellipse is symmetric across both axes, the total area is 4 times the area of one quadrant. When we multiply 4 by pi b over 4, the 4's cancel out perfectly, leaving us with our final, elegant formula. The total area equals pi b. This is a beautiful result, as it looks very similar to the area of a circle, just with the radius replaced by the semi-axis b. Real-world application example. Now that we have mathematically derived the formula for the area of an ellipse, let's see how this applies to a real-world engineering problem. Imagine a scenario where an architect is designing a semi-elliptical arch. As we've discussed, elliptical shapes are frequently chosen for ceilings or bridges because they are not only aesthetically pleasing, but also offer excellent structural properties. Suppose this architect is designing a window in the shape of an ellipse. The window has a total horizontal width of 10 meters. Since we know the total width represents 2 times the semi-major axis, we can say 2a equals 10, which means our value for a is 5 meters. The total vertical height is 6 meters, which represents 2 times the semi-minor axis, so 2b equals 6, giving us a value for b of 3 meters. To determine exactly how much glass is required to fill this window, the architect needs to calculate the total area. Let's walk through the calculation steps together. First, we identify our semi-axes from the dimensions provided. A equals 5 and b equals 3. Second, we use the formula we just derived in the previous slides for the area of an ellipse, which is area equals pi times a times b. Third, we substitute our specific values into the formula. This gives us area equals pi times 5 times 3, which simplifies to 15 pi square meters. Finally, to get a practical number for ordering materials, we calculate the approximate value. Using pi as approximately 3.14159, we find that the area is approximately 47.12 square meters. Before we move on to some common pitfalls to watch out for, keep in mind how much easier this was because we used the derived formula rather than attempting a complex integration from scratch. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. I've seen many students make these specific mistakes in exams, so please pay close attention to this slide. First, the most frequent error is forgetting the multiplier. When you set up your integral from 0 to a, as we did in the circle and ellipse derivations, you are only calculating the area of a single quadrant. It is very easy to finish the calculation and stop there, but remember, you must multiply that result by 4 to account for the entire figure. Second, watch your limits of integration. Some students prefer to integrate from negative a to positive a. While this is mathematically valid for finding the area of a semicircle, it often leads to much more complex calculations. As we've seen in the previous slides, it is much more efficient and less prone to error to use the limits from 0 to a and then use symmetry to scale the result. Third, when working with ellipses, be careful not to confuse your a and b values. Always ensure that a is correctly associated with the x-axis and b is associated with the y-axis when you are setting up your integral for y with respect to x swapping. These can lead to an incorrect setup of your function. Finally, keep a close eye on your integration formulas. When evaluating the integral of the square root of a squared minus x squared, students often make mistakes with the inverse sign term. Make sure you handle the arcsign part of the formula carefully during the evaluation step. If you can avoid these 4 traps, you'll be well on your way to mastering the application of integration to symmetric curves. Let's move on to our final summary of the key takeaways. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. First, remember the power of symmetry simplification. As we discussed throughout the derivation of both the circle and the ellipse, when you are dealing with figures that are symmetric about both the x-axis and the y-axis, you don't need to tackle the entire shape at once. Instead, you can simply calculate the area of just one quadrant, from 0 to a, and then multiply that resulting area by 4. So, the total area equals 4 times the integral from 0 to a of y with respect to x. Second, let's look at the specific formulas we derived. For a circle, where the equation is x squared plus y squared equals a squared, we have proven that the total area is pi times a squared. Third, for the ellipse, which we viewed as a stretched version of the circle, where the equation is x squared over a squared plus y squared over b squared equals 1, the total area is pi times a times b. Finally, keep this integration tool in your mathematical toolkit. The heavy lifting in these derivations was done using the standard integral of the square root of a squared minus x squared with respect to x. Mastering this specific integral is essential for solving these types of area problems efficiently. Make sure you review these formulas and the logic of using symmetry, as they will be fundamental in your upcoming assessments.